Hello, my name is Yuni Fuchioka, and I'll be presenting this work titled An Electromagnetism-Inspired Method for Estimating In-Grasp Torque from Visuotactile Sensors. This is work I did during an internship in Omron Sinic X in Tokyo, Japan. This work is about visual tactile sensors, such as this gel-site mini tactile sensor shown in the top left. In particular, we are interested in measuring torques that we apply to the surface of the sensor using analytical techniques inspired from electromagnetism. So starting with a bit of background about visual tactile sensors, these are sensors that provide information about contact, in particular usually between a robot gripper and an object that it is grasping. How it works is there's a camera that captures deformations of a gel as it contacts an external object. In particular, if we embed markers in the gel, as shown in the bottom right, different loading conditions corresponds to different types of vector fields that result from these marker displacement fields. Past work has shown that vector calculus is effective in characterizing the types of vector fields that result in these loads. For example, the vector divergence can be used to characterize the spreading vector field, which arises from normal forces. And likewise, in-plane torques results in this rotating vector field, which is well captured by the vector curl. However, past works did not attempt to analytically model the more complicated vector field that arises from tilt torques. So the contribution of this work is we observed that this vector field is quite similar to the vector field that results from electromagnetism in the case of a dipole charge distribution. And so we use the same calculation we used to characterize such a charge distribution and transfer it to the tactile sensor data and show that this can be used to effectively estimate tilt torque. So how does this work? Again, the vector divergence is related to the normal forces applied on a gel surface. And this equation looks quite similar to Gauss's law in electromagnetism, where the divergence of electric field, denoted by E, is related to the charge distribution, denoted as rho. Now, if we have equal and opposite charge distributions separated by some distance, we have now a dipole charge distribution. This can be characterized by the dipole moment calculation shown here, denoted by P, which consists of a moment integral calculation. And we could substitute Gauss's law into this equation to get the same expression in terms of the electric field. So we can transfer this equation to the tactile data to obtain this equation. Note that a pure torque can be decomposed as two equal and opposite normal forces applied on a gel surface, which is why we see this analogy between the equal and opposite charges in the electric case. So applying this equation to the discretized vector field we obtained from a tactile sensor, we obtain these equations to estimate the tactile tilt torque. And we remark that this is a purely analytical calculation, that we don't need any deep learning or expensive data collection. And we also did not explicitly model the optical or mechanical properties of the sensor. So we expect this to transfer across different sensors. We test this through this experimental apparatus shown here. Here we have the Visuotactile sensor mounted on the fingers of a robot gripper, and we have this plate with a FT sensor embedded in it. And when a human applies quasi-static torques, such as the ones shown in this time series plot, we obtain this nice linear relationship between the force torque readings and the torque readings from it and the tactile torque estimation provided by our method. And we compare this with another method of analytically providing tilt torque estimates using tactile sensors and show that our method offers an improvement. We also show that this works across different sensors. So in the case of a digit tactile sensor, uh, since the gel geometry is not uniform like the gel site, the estimation is slightly degraded. Nonetheless, the linearity is mostly conserved. We also show that it works not just for flat plates, but also for peg-shaped objects, which might be useful for peg and hole type tasks. And we also show how it works for a practical robotic insertion scenario consisting of a USB stick insertion. We show how the misalignment of a USB stick within the hole can be well measured with the torque estimated from our estimation method. We show a short video of what this experiment looks like. Here, I'm teleoperating the robot with a joystick so that we can really isolate the kinds of measurements we are looking for. So in terms of limitations, unfortunately, this method is limited to the case of in-grasp measurement. So when the visual tactile sensor is mounted to the fingers and the fingers is grasping something, because we need to zero the vector field after grasping it, because otherwise we don't get this nice dipole vector field. Dipole vector field, since the vector field is instead dominated by the normal force component. And as with any analytical technique for analyzing visual tactile data, it's quite sensitive to incipient slip. So this is where non-uniform slipping happens between the grasped object and the tactile gel. And this is where deep learning might be more attractive to characterize these highly nonlinear effects. As you saw in the previous video, the control of the robot was human teleoperated, so future work could involve using this torque estimation for automatic feedback control. So to conclude, we propose the tactile dipole moment as a method to estimate tilt torque from visual tactile sensors, and we devise a series of experiments to show its potential practical utility and providing useful information for robot control. So thank you very much for listening.